And I think, yeah, you can start whenever you want, Torsten. Thank you. Thanks again.
Okay, thank you. The obligatory question, can you hear me well, and can you
Yes.
see my screen, and can you see my pointer moving? All
Yes.
yes? Okay,
Yes.
perfect.
Thank you.
Thank you, Danilo. Yeah, so my name is Torsten Hoefler. I'm the professor at ETH Zurich, directing the Scalable Parallel Computing Lab, and today I'm going to talk about large-scale deep learning. And this is actually I'm going to summarize a whole lot of work in somewhat of a keynote style talk, following Rosa's very great talk that she gave on the overall setting of how to run workflows in high performance computing. I'm following now a little bit more of a deep dive with how to dive into scalable deep learning, so to run deep learning workloads on these very large computing machines. And of course, in order to run deep learning workloads on very large computing machines, we need very large applications first. So let me motivate this a little bit with one particular application that is representative for a large class of emerging workloads. And this is training the GPT-3 model, which is an extremely large model. So it has 175 billion parameters. I can't go much into detail, but it costs it somewhere between $6 and $12 million to train. So the single model training is a multi-million-dollar enterprise simply in hardware and energy. So that does not include the people cost that was actually that had to be put in place. And the result was a paper and actually an interesting product. I have tweeted a little bit about it. So if you care about this, actually training this network took 314 zettaflops, and then there are some other interesting points in there. Last year, and that was a couple of years ago, so that was, well, not a couple of years, but about 2020. Another interesting insight that happened last year was this CASP challenge that you have probably heard about. The idea here is to predict protein structures with deep neural networks, or not with deep neural networks, but predict them in general with simulations. But Google has tried deep neural networks, and see there what they did is they actually, with their AlphaFold 2 network, they outdid the next best competitor in this long-running challenge. It's a biennial challenge, has been running for more than a decade actually. They outdid it by a factor of 2. And this is quite amazing. So they used a network architecture. Both of them use a network architecture that is called BERT, or is very similar to a network architecture called BERT. The technology behind this are transformer networks. Now we are going in 2021, we are going into actually productizing these things. We are moving them into the Chinese language area. So a team from Huawei has trained a very similar model, in fact, slightly bigger model, with a very similar setup, and then achieved a very interesting result for the Chinese language. And unfortunately, I don't speak enough Chinese to really interpret it, but it's of course extremely interesting. That was just a couple of weeks ago. So how do we achieve this? Well, we achieve this by heavy investments. Microsoft alone is pledging $1 billion to this company that ran that ran GPT-3 in order to get to artificial general intelligence, so human intelligence. So how do we actually emulate very large like brain-style models? They built a specialized supercomputer for it, which has about 3 exaflop if you do the math. And then there are more and more investments coming. If you've watched Jensen Huang's GTC keynote a couple of weeks ago, he was announcing a Swiss system as the world's fastest supercomputer for AI, which is about 20 exaflops of AI, so significantly faster than the existing systems. And more, we are moving into more and more specialization in these systems towards general intelligence. So these are incredibly large systems. These are full supercomputers being used for training single models that are running brain-like tasks in some sense. So, and this is what I'm talking about. If you're looking at how these models look like, this is actually not too complicated. It's a transformer model with multiple encoders, again, in the structure of the BERT model that I mentioned before. In order to train this model, what do we need? And this is the 3 pillars Danilo also mentioned at the beginning. We need high-performance I/O because we need to somehow read the data. In the case of the GPT-3 model or the BERT models in general, it's textual data. So we're essentially reading the whole intranet. This is how these models are trained. You just hook them up. Okay, that's exaggerated, but you could imagine that you hook them up to the internet, and everything I say here immediately goes through the model and is added to the knowledge base of the model. That would actually be technically possible. So we need very fast I/O. We need very fast compute, because here in these language models, the I/O is not too important. That's more about CNNs and image models, but still we need to care about this. The compute is much more important, and compute is mainly data movement today. And then if we train them on a very large distributed system, we need to worry about high performance communication. So very large clusters, 10,000 plus GPUs, we need all kinds of forms of parallelism. What I want to do in this talk is I want to give you an overview of some interesting ideas that we've been developing in my lab in order to tackle each of these three challenges. And in fact, I believe solving each of these three challenges, at least for the foreseeable future, moving forward to these like about 10,000 GPU style models, or maybe even 20,000. So let me start with high performance I/O for deep learning. That's a that area in the lab is run by Nicole Dryden, and the specific work included a student, Roman Böhringer, as his master's thesis. So here the idea, or the observation is that if you run a ResNet 50, you need about 3.8 gigaflop for the forward pass for inference, 3 times that for training, as for pretty much every deep neural network. Then if you train this on the ImageNet dataset, you have about 150 gigabyte for 1.3 million images, which means your average image is of size 115 kilobyte. The range, in fact, goes from 500 byte to 15 megabyte. In case you were wondering what the 500 byte image is, it's this one. It's supposedly a nail. However, my biological neural network would not really recognize this as a nail, but artificial neural networks apparently do. So if you look at the performance on an A100, we get about 2.9 thousand samples, so images per second throughput, which means we need on a single A100 GPU, we need about 300 megabyte per second random access of size 115 kilobyte. If you do the math, you will need about 2 SSDs, like reasonable performance SSDs per GPU, per A100 GPU, in order to give you that random access. And now for larger problems, 2.8, 2 to 4 times that much for scientific problems. Now, if you train this on 1,000 GPUs or on thousands of GPUs, you would need, let's say, 2 or even 4 times 1,000 of these SSDs. So you would need to coordinate a very large number of solid state drives. And we know how to do this in high performance computing. We have lots of parallel file systems that we have developed in the past. And this is great, then we can just use those. Well, but the question is, do we actually need those? And the answer is not really, maybe. Most likely not really. Because how does deep learning actually work? Deep learning workloads, they randomly sample their input. So what does randomly mean? Randomly actually means that it is a pseudo-random sequence with a fixed seed. So it's not really random. It is not really predictable, but it's deterministic once you know the fixed seed and the pseudo-random sequence, which means we have a clairvoyance of what is coming. So if I'm sitting there as a training process, I will know what's coming in 100 iterations. So I can pre-compute that schedule. And if I pre-compute that schedule, I can build a near optimal prefetching system, what we call no PFS, and this is pun intended. So now let us explore this idea a little bit. So if we had this no PFS, which could act as a distributed cache, where each node keeps an in-memory cache, fully knowing about the future of what's coming at each node. Right? So we can pre-compute all of these things. And now if you simulate this and we look at how often is each sample accessed at each node, remember this is random. So we are expecting some kind of Gaussian-like distribution here. And if you look at this, we actually see it is reasonably well distributed. We find that some samples are even accessed 18 times. Not many. On average, they're accessed like 5 to 6 times, which is still significant. So what we can now do is we can look at this distribution. We can pre-compute that distribution. And we can now select the samples that are going to be reused very frequently in the future. And this is what we mean by distributed cache with fully clairvoyant, knowing about the future prefetching. And then we allocate for the highly reused pieces, we allocate the fast, limited size storage class, the fastest. And for the less reused pieces, we allocate the next storage class, and so on. So this is a very simple idea. We have this all implemented. I don't want to go into too many implementation details. I just want to present you some results on the Pitt-Stein system and also later on the Lassen system at Livermore. If you now look at the batch time, so the time per batch iteration spent with 3 different systems, so PyTorch, the PyTorch data loader, the PyTorch data loader together with the DALI NVIDIA optimized loader, and our no PFS. And I just want to focus you on the largest run here, 256 GPUs on that system on 256 nodes. We can actually see that the difference between the expected value, where we are here, and the maximum value is more than 100 times. So meaning that some batches are more than 100 times slower than other batches if we do not prefetch the data. And this is just due to the general flakiness, I would say, of high-performance file systems. So this is just kind of a normal observation. If you sample randomly very small files from a very large data set. So this is just a normal fluctuation of a POSIX-style access. And if you run this on the Lassen computer, it's basically the same. There's a 150x difference between our no PFS runs and the normal PyTorch runs. And this is really the same phenomenon here. So this really means if we use this knowledge about the future, we can have a near optimal prefetching decision, which makes training much, much faster. Now, the batch time may not be the significant factor here, but if you're looking at the epoch time, this is now the whole application runtime, so to say, we are gaining a factor of 2 to 4, depending on the setup. So usually for very large runs, we achieve a larger, here is very prevalent. If you look at the PyTorch time and the no PFS time, that's a factor of nearly 4 here at 1000 GPUs. Really exploiting that feature that we just know about the future. So with that, I would like to move on. I'd like to close the high-performance I/O because somewhat, if we know about the future and if we can compute this near-optimal prefetching mechanism, I believe we can solve most, if not any, training workload on very, very large-scale systems because we don't even need a parallel file system, essentially. We don't need a POSIX-style parallel file system. We can just prefetch the data optimally from even local disks. So if we just had a like a loosely connected system without any shared state, we could still implement this very, very efficiently. The second ingredient for our very large-scale deep learning is now high-performance computation that we need. That is a little bit more complicated, but at the end, it means that deep learning is really high-performance computing, and we know exactly how to do this. And what this means, high-performance computing for a while, if you haven't been asleep in the exascale discussions, is really a data movement problem. So computation is nearly free, data movement is getting more and more expensive, and data movement is actually moving towards being the absolute bottleneck in our computational systems. So far, in deep learning, it has not hit yet, but it did recently. And it did recently because these structures that we are seeing here, like this BERT encoder, which is nothing but a high-performance computing application in my view, many of those are in fact very similar to matrix multiplications. Like these linear layers you're seeing here is more or less a matrix multiplication. It's a tensor contraction, really. It's a four-dimensional matrix, a four-dimensional tensor that's contracted along different dimensions. But at the end, you can always reformulate these things as matrix multiplications if you want, and then compute them with our well-known BLAS calls. Then there are some other pieces which we call statistical computations here that are not matrix multiplication, like these softmax computations. But remember, we are training extremely large models, 175 billion parameters, $12 million to train. And now let us look a little bit more at the distribution of what is happening in there. So as I mentioned, these tensor contractions, really matrix multiplications, they have been highly optimized in the past. In fact, there's NVIDIA introduced specialized tensor cores, which launched some kind of intensive discussion about their use in the high-performance computing context. If you listen to Satoshi Matsuoka and Jens Domke making these arguments, they're not too useful in HPC. However, they have been incredibly useful in deep learning. And they have been so useful that you can solve 99.8% of the flops in 60% of the runtime. And this is highly optimized. They're extremely efficient. So what does this now mean? Well, this means that 0.2% of the remaining flops actually occupy 40% of my runtime. So even if I make these tensor contractions infinitely fast, I will not get much more than a speed up of 2. So that is actually a problem. So now we are data movement bound if we assume that these tensor contractions are just handled by the tensor cores. So what we find is that we actually tune for this data movement specifically and explicitly. We can achieve 30% speed up over PyTorch. That's kind of the default implementation. It is tuned, 20% speed up over TensorFlow, and 8% over a manually tuned version of exactly that encoder. Right, so with all the same parameters, which saves about up to $3.6 million for the GPT-3. Of course, that's easily paying for the PhD student who did the majority of this work. So how do we do it? Well, we do it by looking at the data flow graph of this thing. So you've seen on the previous slide somewhat of a cartoon how it looks from a data science perspective. Here we see a more detailed cartoon how it works from a data flow perspective. So where does the data come from? So these oval pieces are, I don't have enough time to explain this in detail, but these oval pieces are arrays. Then we have these Einstein summation style tensor contractions. Here we see the number of operations. Here we see the operational intensity for each of those boxes. We are using the data-centric parallel computing framework that's developed in my lab in order to get to views that are very similar to this. But then the key, what is the key? Now, as a human, we can look at those. We can see which ones are I/O intensive, which ones are medium I/O intensive, and which ones are very I/O unintensive, like computationally intensive, like all the tensor contractions. So for those, we are looking at different data layouts. So if you have a four-dimensional tensor multiplying it by another four-dimensional tensor, or contracting it with another four-dimensional tensor to be precise, you have many, many different ways you can arrange the data in memory. You can lay it out dimension 1, dimension 2, dimension 3 times 1, 2, 3, or 2, 3, 1 times 3, 2, 1, or any of these combinations. So if you actually look at the performance of these different combinations, you see that there is quite a quite a large spread between those, spreading by more than an order of magnitude in this particular example. So you want to find the best configuration up here of the memory layout for each particular contraction. Furthermore, you want to fuse these operations here together in order to minimize the data movement between these different operator kernels. So somehow you want to, you can now imagine different fusion strategies like taking subgraphs and merging them into the same loop, essentially. That's what happens programmatically. And now we also see that there is an order of magnitude, or nearly 2 orders of magnitude, spread between the worst fusion version and the best fusion version. So now we have these two data layout and fusion strategies, and we combine them into a relatively complex configuration selection graph. I don't have enough time to talk about this, but the idea is now pretty clear, right? We look at all of these configurations, we look at all of these configurations, and we find the shortest path through this graph, finding the best data layout and best fusion strategy. And with this we achieve the significant speed up over state of the art. The paper was published at MLSys this year with Andre, with my student Andre, and he has been implementing all these great things. Excellent. So now that we have the high performance compute, and by the way, this generalizes to a large number of applications. It's always essentially the same. And now we are working on actually automating this in the DACE framework to move this fully automatically, this more or less manual approach that we had here to the deep learning world. The last part I want to talk about is high performance communications. So now if we scale this to very large clusters, we may just be communication bound, which is just a different form of data movement. Now we need to worry about model parallelism, complex pipelining schemes, and sparsification, all kinds of other things. This is in fact where my team started this work on deep learning in 2017, and our first publication was in 2018 here, where I want to explain a little bit what this actually means to parallelize deep learning workloads, because that may not be too clear to everybody, but it's also really easy actually. So what we have in deep learning, we usually run multiple so-called epochs of multiple different mini batches. So a mini batch is a subsample of my whole data set that I'm using as a statistical unit in order to implement a single iteration in my forward pass, and then compute the gradients for the backward pass. I don't want to go into too much detail, but that's kind of the unit of computation and the unit of parallelism, in fact. So I can fix one form of parallelism, that is data parallelism, where I'm copying the full model to different execution units, and I use different inputs from that same mini batch in order to compute those in parallel on these different units, like the green one, the blue one, and the red one here. So that is some form of parallelism. That parallelism is, of course, limited like any parallelism. The second form of parallelism is pipeline parallelism, where I can now, in addition to the data parallelism that I mentioned up here, I can now distribute each of these models, the first layer of this model, so these are the layers here, the second layer of this model goes to a different accelerator, and the third layer of the model goes to another accelerator. So now we already have a 2D distribution. I can distribute the data I can use data parallelism to distribute across the data, and at the same time, I can use pipeline parallelism to build somehow of a 2D torus distributed system or distributed run in order to exploit that pipeline parallelism, which is very beneficial. This is, by the way, how you run these very large models. In fact, if the models are so large, which is the case for GPT-3, that a single layer does not fit an accelerator, we have to parallelize that layer as well. And that is getting pretty annoying because you don't necessarily want to parallelize a layer because, as I mentioned, most of them are matrix multiplications. And parallel matrix multiplication is not easy because the communication volume is very high. But in extreme cases, you also need to cut these operators and distribute them across multiple accelerators, which now means we have a three-dimensional layout. So we have to combine data parallelism, pipeline parallelism, and operator, or sometimes called layer parallelism. Sometimes they also call it model parallelism, but that I find highly confusing. So now, once we have cut the model in these three different dimensions, we actually see that we can now run it in a large number of different configurations. So what I want to emphasize a little bit, for each of these layers, you have a lot of optimization opportunities. And I want to talk a little bit about what we can do for data parallel distributions. Because data parallel is the highest communication bottleneck traditionally in deep learning. What this actually means is that if you have these distributed model copies here, every now and then, because you run the examples separately through these copies, every now and then you need to update or average all the weights across these model copies to be consistent. By every now and then, I mean usually every iteration if you want to be strongly consistent, meaning that every time you update the weights, you need to run an all reduce operation essentially between all these model replicas in order to exchange all the weights. How large is that all reduce operation? Well, as I mentioned, you need to exchange all the weights. And the size of the weights for GPT-3 per accelerator could or is usually in the multi-gigabyte range. So you would need to run an all reduce of multiple gigabytes every couple of milliseconds. So that is quite expensive. So the question is, well, can you actually afford this? Do you have enough memory bandwidth? The answer is typically no in high performance computing systems today. If you have a fast node, then you will be highly bottlenecked by the memory bandwidth. However, it turns out that of this communication, if you do the communication not on the model weights, but on the gradients, which is the default, you can also do it on the model weights, as I'll be talking about later. But if you do it on the gradient values, which is now the error on the back propagation during the network, you can throw away 90 to 99.9% of these values. By throwing away, I mean you store them locally, you just don't communicate those. And you can still achieve a similar accuracy. And so you remember the values you don't communicate locally, and you just send the top 10% or top 1% or top 5%, that now depends on your model. And then, of course, you have reduced your communication volume significantly. And then we have actually in NeurIPS 2018, led by Dan Alistar, a dear collaborator, we have proof that this actually still converges. We have shown this empirically, and we have also shown this for, I mean, we have shown the assumptions in our proof, and we have also shown this for real networks that it really converges. So this is the theory. But now to the practice. How do you do this in practice? Because in practice now, if I have these 4 different training processes, I have 4 different sets of weights. And now this is my, gradients. These are my sparsified gradients, meaning the black area is whatever is non-zero and the white area is whatever is 0. So here in this case, it's a little bit more than 10%, but for visualization purposes. But of course, at each node, I will have different gradients that I select based on their magnitude. And so now I have this problem from just a pure systems perspective. If I'm summing these gradients, I will, of course, densify them as I sum them in this butterfly-like pattern, for example. And at the end, the gradients will be more or less dense. So somehow that is not easy to implement. MPI does not support that operation by default. So what we did is we implemented it. We call this Sparse ML. It's a pretty advanced scheme because you also have to match all these indices now and the GPUs, and it's a lot of systems work that I'm skipping here, a lot of great work done by my students. But the key idea is that we actually switch from a sparse representation in the middle when the gradients densify a lot to a dense representation. Because a dense, if you store a dense vector in a sparse representation, that's one of the worst things you can do. So somehow you need to switch as the vector densifies. So we have demonstrated that in practice with a Microsoft Speech production workload where we went in distributed training from a 2-week runtime to a 2-day runtime. That was quite impressive, but mainly because they ran it on a system that had a really weak network. And you can see here that the speed up, for example, on the Pitt-Stein network is relatively little because that's a high performance computing system with a lot of bandwidth initially, I mean, to start with. But if you run it on an EC2 instance, you get immediately a 20 times speed up because, of course, at that time, EC2 was relatively slow from a bandwidth perspective. So now it depends on how much you're really gaining from this. Okay, so now let me switch gears from the sparsifying approach to dealing with other problems during training. Especially if you go to large-scale training, you may have that problem of unbalanced workloads. So specifically, some training scenarios, they cause very different work in different training examples. And video inputs are one of those. So if you want to train on videos that have different lengths, like in the YOLO dataset, or in the UCF 101 dataset with the YOLO network, this is a YouTube dataset, you will find that the number of frames per video range from 29 to 1800. So that's a huge distribution here. So that's just a distribution of number of frames. Now, of course, if you run this through an LSTM network on a P100, you will kind of translate that huge distribution in video frames to a huge distribution in runtime. So now each of your training processes takes a different time in order to process the forward pass, which is of course a total nightmare if you're running this on 10,000 nodes, because at the end, if you're doing the backward pass and wait for your all reduce, you have to wait for the slowest guy. And that you see the range here going from pretty much 0 or from somehow 200 milliseconds through 3 seconds, right? So that's now a bit of a problem. So if you do this in the synchronous SGD to just visualize this, we would do the compute pass. The compute is highly unbalanced. We would wait, then we would run the all reduce, because the all reduce only finishes or even only starts in most of the cases once all the processes arrive. Then we would do this again. Then we would again wait. Then we would again do the all reduce and so on. Then you see about half your time in this comic here, or this view graph, is spent waiting. Not a great idea. So what we did is we looked at the eager SGD, because as I just mentioned, you can just throw away much of your data. Why don't we just ignore some of the gradients and communicate eagerly, in the sense that when about half the nodes arrived, and I will tell you how I get to the half the nodes arrived, I just start an all reduce and I ignore the gradients of the nodes that have not arrived yet, and I keep doing this. Right? So the idea is now, statistically seen, we want about half the gradients to be correct, and then we trigger an asynchronous all reduce that'll just use the gradients that are correct and do some interesting math with the other gradients that are not correct. And you can read this in the paper. I don't have enough time to explain it, but I want to give you the idea. And we can do this asynchronous all reduce with a smart NIC, for example, with another project in my lab, like streaming processing in the network, where you can implement all of this in the network card for free. In fact, we implemented it as an asynchronous thread. So now, if you compare this performance for this specific LSTM on this UCF 101 dataset using 8 GPUs, you see, I mean, you can look at this for a while and interpret it, but I'm slowly running out of time. You see that you actually get a significant speed up if you're willing to reduce your performance, so your accuracy down to 60% from 70%. So you get 60% speed up, but you get 30% speed up if you do this majority triggering and you don't lose any accuracy, essentially, or not much. So this is an interesting idea. Now you can actually go further. You can say, well, actually, if I want to improve this further, why do I even run a full all reduce here? Why do I not just run partial sums? So for example, here, we have the same schedule as up here. And here I'm summing in each iteration only half the nodes, and then the other half in the next iteration. And then after multiple iterations, I do a fully synchronous update, which is pretty much the same as somewhat of a distributed version of this top K SGD method. We have a proof in the paper as well that works. It's it's a very similar proof, has very similar assumptions, and actually works really well for deep reinforcement learning methods. Because in reinforcement learning, you're playing against yourself anyway. So if you lose some things, you will actually you will not get into too much trouble. Right? So that is quite important here. And here we have on the blue scale, so we have the score of how the agent performs and the training time here. And here we are dropping a lot of data in this WAGMA SGD, but still the performance of the agent, which is what matters at the end. I don't really care about how much data the agent has seen or how much correct data it has seen. I care about how well it performs on a test data set is the highest among all the different techniques here for a limited training time. So we perform significantly better than the other ones. So now let me talk, after talking about some ideas about high performance communication, let me put something else in your mind, because I find that pretty exciting. So now if you want to train really large models, so really models that are as large as my brain, well, my brain may not be the largest one here, but still it's pretty large. The brain is not fully connected. The brain is very, very sparse. So actually, all the models I talked about, they do dense matrix multiplications, so dense tensor contractions. But I want to train a model that is larger than the largest computer can hold, and in a dense configuration. And the only way to get there is really to go with fully sparse training, which is a very hard topic that is not fully understood in the community today. So the question is now, well, why are DNN computations dense? Well, because we know how to do it. And we may actually move, mainly for technical reasons. There are many, many technical reasons that are even of kind of mathematical nature, because SGD works really well on dense, and I could give another 2-hour lecture about how sparsity. I just want to tease you a little bit here. But the fundamental idea is that, or the intuition is that not all features are always relevant. So I can just drop some features, like in this sentence here, I'm dropping about 30% of the letters and you still understand what the sentence means. Which means if you're talking about artificial general intelligence, that is one of those ways we can use. We can just drop some of the neurons in the network, some of the weights, and we can simply use the space more efficiently. So this is some form of compression. It's not a lossy compression. Most of us will be able to decode it completely to the fully correct result. And you can show this, of course, for machine learning workloads as well, where you can train a 95% sparse ResNet 52, which has essentially the same quality and is up to 20 times cheaper than the dense version. So actually, if you really care about this, together with some colleagues, I wrote a 90-page survey about sparsity methods in deep learning. Turns out that there is much more work than I was thinking when I started this. So I spent about 6 months writing that survey, and some people call it a book. But if you care about this, I would look at this. So now, just to give you one more teaser, we may want to go to extremely high-dimensional sparse models, because somehow in high-dimensional models, I can capture much more information, which is somehow the inverse of the curse of dimensionality. You know the curse of dimensionality, it's a problem if you want to sample very large spaces, but you can invert that because these large spaces have a lot of information in it. And you now want to encode, take that information or encode the information into this very large sparse space. So this is a relatively complex topic. People have worked on this, so about 25 papers exist. But some of those things are, for example, dynamic sparsity, where during the network training, we are starting with a random initialization, which is also called the birth brain. Then we grow and add neurons pretty much randomly, like what happens in humans, by the way. So when we are very small, our brains grow denser and denser and denser. Furthermore, then later, as we go towards the adult brain, we are actually sparsifying more and more. So we're losing more and more connections as we age. And so you can use that as a training strategy. You could also start with a fully static sparsity schedule where you basically train with a fixed sparsity configuration in your network. And then there are many, many, many ideas we could talk about here. But since I'm slowly going towards the end of this slot, let me just skip this. So with that, I would like to close my talk, but I would like to use the last 2 minutes to talk about or mention something that was actually mentioned at the opening, weather simulation. So one of the big scientific use cases that we are working on is really trying to understand how to predict the climate and the weather in a deep learning context, or with deep learning technology. And the idea here is that actually the way we simulate weather today is with an ensemble. So we start from initial conditions like the temperature, and then we are somewhat, these initial conditions, they follow some distribution. So they are not fully accurate. Our sensors have uncertainty. We don't have all sensors at every place, at every spatial location on the planet. So there's always uncertainty in these measurements. Now we permute these slightly, and then we run the forward simulation with many, many simulations. And now we get an output distribution. And of course, it's a chaotic process. So this may go arbitrarily far away, but we get an output distribution that we want to characterize. In fact, we're using this for the weather forecasting directly in Switzerland. So in Switzerland, you get your certainty of rain, for example, partially due to the work that one of my students has done to move this on a GPU. But what we do now is we don't run the simulation on a GPU. We run a small subset of these trajectories, not the full 50 that ECMWF would be running, but we run something like 10. And then we use a deep neural network in order to predict this output distribution from the limited sample of the output distribution you can see. So we use a ResNet for this. Actually, you can do something more. You can even correct the expected value of that output distribution or the bias with real observed data. So for this, we use a 3D unit. So these are somewhat preliminary results that we apply to very simple deep neural networks, and it's a very simple setup, and you can fully reproduce it, by the way, our paper, you can just download it. We applied it to a simulation of repeated simulation of the tropical cyclone Winston that actually happened in 2016 over Fiji. And you can see, it's relatively hard to see, but you can see that if we compare the ton ensemble run versus measurement, there's a pretty large inaccuracy at the eye of the cyclone because the resolution is not high enough. So the redder the verse, the more blue, the better. And here, if you run more ensembles, you see that this gets better. The blue gets better if you go from 5 to 10 simulations. But if we actually use 5 ensembles plus our DNN, then we get even more blue. So we get a higher boost than out of these ensembles. So with that, I would like to end my talk and go back to this overview slide in case you have any questions. Thank you very much.
Thank you, Torsten. So we have 5 minutes for questions. Okay, actually, if you want, Carl, you can open your mic and raise your question directly.
Okay, great. Thank you very much. So thanks for a great talk. Super interesting things you took up. So first question relates to these 3 dimensions of parallelism that you mentioned in the first part of the presentation, which, as far as I understood, relates mostly to accelerating individual SGD steps in the deep learning process. So my question is what your view is on asynchronous parallelization of SGD and connections and orthogonality to this more step or iteration-wise parallelism. And I can maybe go ahead and answer the second also at the same time. So when it comes to unbalanced workloads, I had a thought about if it's possible to utilize the fact that you know your future here as well, and also hence the sizes of these batches for scheduling purposes.
Mm-hmm. So the first question on the asynchronous SGD, well, actually, what we do is somehow asynchronous SGD, and so we are deferring parts of the data. There's so many different definitions of asynchronous SGD, but if you think about our framework, we are actually deferring parts of the communication to later, right? So we do accumulate the gradients that we don't send into local buffers, and eventually they will be large enough to be sent. So this is just one form of asynchronous SGD, but per element asynchronous. So some elements are sent synchronously, the largest ones. The smaller ones, they wait until they accumulate and then they're sent synchronously. And every k iterations, which is what I didn't say, k is about 100 or so, by you have to hyperparameter, right? Then we do a full all reduce. So I do like these asynchronous methods as a research topic. There's one thing, as much as my heart bleeds saying that, that I have to say about this, that in industry they're not super highly used. So it seems that for large scale training, we are still waiting for the expense to be so high that you have to use them. And this is kind of my point here. So we have a whole lot of different techniques developed, also this WAGMA SGD or eager SGD. They are all forms of asynchronous SGD training. So they fit into this idea there, but there are hundreds of papers of asynchronous SGD. So this is not, I don't want to dominate this here. It's just what I know best. The second question, if you can use clairvoyance to deal with a workload imbalance, that's a very good question. So we've actually started to look at this, but well, it turns out that this is already working well enough with the asynchronous approach. Because what would you do with clairvoyance? Now, what if you understand this? You cannot prefetch the data. So we are still lacking the exact idea how to deal with this. We could probably redistribute the data to make it more balanced. That would be one idea, but it's also expensive. So the prefetching is somehow simpler because you have a larger buffer of time to do this. You just overlap the prefetching with the computation of these things. Does that make sense?
Yeah, definitely. Thank you very much for the answer.
Thank you. We have time for another question. Parijat, you have a question, right?
Yes, one question. So thanks for a very interesting talk, Torsten. So regarding eager SGD, so I have a question, like when you say eager SGD, is it eagerness at the level of different workers, like, or at the level of mini batch? So if you're waiting for k gradients, then the k has to come from different workers, or they can come like 2 from the same worker who is faster, like 2 mini batch, right?
Oh, I see. So we do this in this setup. I should probably go back. Oh, I can't go back. Oh. Why can I not go back? No, I can go back. This is a bit more complicated than I was making it seem. So if you look at this, each worker, so these are the workers here, right? So each worker is participating in each all reduce. And these all reduces are not run by the main thread, but they're run by some other thread, for example, on this SmartNIC. So this all reduce will actually set up the next all reduce asynchronously, like asynchronous from the main thread. And so this now means that they will always participate. Right? So this is still bulk synchronous in some sense. It's not really, at least for these two different threads of progress, it's bulk synchronous. But now some of these, like this guy here, will not see the right gradients, right? Because the right gradients will only be finished here, but he has to communicate here. And now the question is, what do? Do we send outdated gradients from the last iteration? Or do we just scale down these gradients? So we have multiple different techniques in the paper that we could look at. So one of them is just to diminish the contribution of the gradients that are stale, because we know which ones are stale. Another one would be to just don't send the stale gradients, but then divide by the number of non-stale gradients you got. So you just ignore the stale gradients essentially, but they would still play in the communication, because they must play in the communication, because after all, this red piece is again a butterfly pattern. So we cannot easily let somebody out of that butterfly pattern different in each iteration, right? Because it also differs with the stale gradients. Like in this guy, for example, the same worker here in the second iteration has non-stale gradients, right? So this pattern of who's participating would be changing in each iteration, and just figuring out who's participating is too expensive, so we just run the whole thing. Does that make sense?
Yes. So I have one more question regarding the last slide on simulations, simulation-driven deep learning. So I want to, this is a general question, that whenever we do simulations to collect data and then you train it a deep learning model, then there are always some assumptions made when you write a simulator, right? When you simulate it. So how much is the error in the simulation itself from the or the assumptions in the simulation itself, they affect because your model is learning from that data, and so whatever ground truth the model knows is a ground truth coming from simulation. So is it good to have some type of error, because that acts as a regularization technique and your model can generalize better? Like you understand what, like does it help in generalization to be always be little away from the reality?
That is a good question. I mean, I would be very careful to say that simulation errors help generalization, because they may be biased as well, right? So they may just shift me away. They may not be random with a zero expectation. If they're random with a zero expectation, then this may be a good idea, but I don't know. So what we are here doing is in fact, this is the first step. So we are doing post-processing. So somehow we are still running the full simulation, and then we take the output of the simulation to predict that output distribution. Right? So we are not running the simulation with a deep neural network. This is just after the fact. And now the simulation errors that we are seeing in the simulation, well, they will be part of that output distribution, very much like they're part of the original output distribution that we ran with more ensembles. So essentially what we are doing is we're just running less ensembles here, because these ensembles are extremely expensive. So if you can go down from 50 to 10, that is immediately also $1 million saving. Right? And actually our hope is that we can stick to 50, but then get a much better accuracy as if we used the network, if we were running like 100 ensembles or things like this. So just improve the accuracy, but that has to be shown. So far we haven't shown that. We have just shown comparisons with the existing ensembles. Furthermore, the second point here is that we can, even like you mentioned, that we only have simulation data. That is not fully true. In that particular example, we have the ERA5 data set, the resimulation data set, but we also have observation data. So when we train this 3D UNet, we are actually correcting the error of the simulation itself against real observations. So the simulation has a bias, as I mentioned, right? This is why I'm saying I'm not sure if this can act as a regularizer, because we know it has a bias. But this bias, we can learn the difference between the output of the simulation and the real measurement, we can learn in the deep neural network, and we can use this for the bias correction. This is actually pretty strong. Does that make sense?
Yeah, that makes perfect sense. Yeah, thank you.
So it's both post-processing. One corrects the bias of the simulation, where the simulation is just wrong or slightly wrong, but in some form of regular pattern that repeats across multiple predictions. And this happens a lot, actually, because the models are not perfect. So, for example, there is a tree over there, but the model does not know, and there's a mountain there, and things like that. This is not captured in the model. This, the deep learning model will figure out, because it has so many parameters to just learn all of that. And the second case is then where we are learning the distribution. So we do both together in these results down here.
Thank you.
Thanks a lot, really, Torsten, again. And I will leave the floor to Vinod, who will moderate the next talk. So